start yours. Okay, thanks. Por, take it away.
Okay, so it's a pleasure to have Xiao-Gang here today, who will be telling us about 3+1D topological orders by classifying unitary, non-degenerate, braided fusion 2 categories. Xiao-Gang, please take it away.
Yeah, thank you. Thank you for the invitation. I really enjoy this seminar series. It's a very timely and a lot of very interesting talk. Today, I'm going to talk about a classification of a 3+1 dimensional topological order. You know, in this seminar series, we heard a lot about the symmetry, the generalized symmetry, higher symmetry, the non-invertible symmetry, and etc. So it turns out that those symmetries, this particular generalized symmetry, may not be described by a group or higher group. Instead, the symmetry is described by a topological order in one higher dimension. And actually, there's a lot of equivalent theory. So the symmetry can be viewed as a non-invertible gravitational anomaly, or the symmetry and its dual symmetry can be put together and to get a more complete description. And this together led to the picture that which corresponds to topological order in one higher dimension, which is also a non-degenerate braided fusion category. And there's also a algebra of local symmetry operator point of view. So there's also the braided fusion category hidden in the algebra of local symmetry operator. So all those developments kind of led to the picture that the symmetry have there's a more general way to describe the symmetry rather than using a group. So instead of discussing those connections on this new point of view of symmetry, today I'll concentrate on the topological order in one higher dimension. So in this respect, it describes a symmetry in one lower dimension. So you can view topological order as a replacement of group theory, which describes symmetry in one lower dimension. So in particular, the topological order in 3+1 dimension discussed today will describe a symmetry in 2+1 dimension. So what is topological order? Topological order basically is the equivalent class of a gap quantum system. So let me just quickly review what is a quantum system, what is a gap state. A quantum system defined by a Hilbert space and a Hamiltonian Hermitian operator acting on the Hilbert space. But however, in many-body physics, or in condensed matter physics, we always discuss system. And in certain dimension, this concept of local and the dimensionality of a system is embedded in the tensor product decomposition of the Hilbert space. So the Hilbert space can be written as a direct product of many smaller Hilbert space. And this smaller Hilbert space can be assigned to the a vertex. And this vertex form a graph. So they have a sense of neighborhood, a near vertex, further vertex. And that's gave rise to the notion for dimension. So this Hilbert space with tensor product decomposition is so-called a local quantum system. And the Hamiltonian is sum of the local operator which act on a single small Hilbert space or in some several small Hilbert space nearby. And usually a ground state is referred as a lowest energy states, the state with the smallest eigenvalue of this Hermitian operator. But actually, in physics, we usually refer to ground state as this linearly degenerate subspace, which is separated from rest spectrum by a big energy gap. So this is a notion of a gap state. The gap state is that we have a window in the spectrum, and below the window there's a nearly degenerate states. Therefore, to say things more precisely, actually, the notion of a gap is not a property of a single system, but the concept of a n go to infinite limit, where n is the number of vertex. And when n go to infinite limit, this splitting of low energy space becomes smaller and smaller, but this window remains finite. And this this nearly degenerate ground states from this low energy subspace, which is more precisely referred as a gapped states. Okay, and then to define gapped phase, quantum phase, we need to define the equivalence relation between gapped state. And this gapped state, this equivalence relation is given by this adiabatic evolution. So we're using this Hermitian operator, which is sum of local operator, to define a unitary operator, which is rotate this low energy subspace in the nearly degenerate subspace. And if the two nearly degenerate subspace can rotate into each other via this local Hamiltonian, then we say they are equivalent. Okay, and in modern days, in quantum information age, people also write this adiabatic deformation as this discrete layer of local unit transformations. And so this became a local unitary quantum circuit. So this adiabatic evolution is also local unit quantum circuit. So therefore, two low energy states connected by the local unitary transformation was regarded as equivalence, and this equivalent class gave us the gapped quantum phase. So the picture really the following: in the sequence of n go to infinity, and we can have we have two sequences of n go to infinity, and each for each n there's a local unitary equivalence, and this define the gapped quantum phase, and which in some sense define the topological order. So this is a microscopic definition of topological order, but this definition have a problem. You know, it's okay for translation invariant system, but if system have no translation symmetry, it's hard to enlarge the system. Because if you enlarge the system, if you double the system, maybe one half system is quantum Hall state, another half is a ferromagnetic states. So it's a non-invariant system. There's a problem with this. So this problem is fixed by generalize this equivalence relation. We say the two quantum states with different size can be viewed as equivalence if one quantum state with bigger size is a smaller quantum state tensor product with the product states. So this DP is a direct product states. It's just a tensor product states of states on each small vector space. Okay, so this will be part of a equivalence relation. Then plus it's a local unitary, they define a bigger equivalence relation, and then the system with the different size are connected. So this actually is a microscopic definition of topological order. So in some sense, a topological order have a kind of precise definition using microscopic theory defined on the lattice. And nowadays, we think this topological order is should be related to the so-called fully extended quantum topological quantum field theory, or some kind of braided diffusion category theory. So those topological quantum field theory and the braided diffusion category somehow is defined for the continuous space or continuous manifold. Okay. But this microscopic definition of topological order is defined on the lattice, on the graph. So the connection between these two definitions already touch a very basic question: how the structure of manifold emerge from a graph, from discrete graph. So this is the famous problem in quantum gravity. But even in topological phase, this kind of issue appears.
Xiao-Gang, can I ask a quick question? You kind of already addressed it, but I just want to ask for clarification. So what are the assumptions you made on the graph here? I guess you need some notion of locality or some notion of dimensionality, right? A general graph has no such notions.
Yeah. Indeed, the graph here. Here the graph is right. So the graph I'm thinking about is I think have more conditions, so that is can locally approximate somehow resemble the manifold. So basically, at least one should have every vertex have a finite number of edge, every edge have finite number of triangle, and also there's there's some other things you should not have a dangling triangle attaching arbitrarily. There's something which is something there, yeah. But I think most important thing is there's some connectivity thing, yeah. Yeah, I don't know enough of graph theory to really describe this general formulation.
But since you also mentioned phases, a general graph doesn't even have the notion of phases. A graph is just made of vertices and edges. So I guess you actually have more structure.
So basically, I like to have a graph which have enough structure we can define the dimension of a graph, which have integer dimension.
Okay.
And this is important actually. So graph should have certain regularity, which so that the dimension is somehow well defined. And the graph is more general, so you have a graph with have a fractal shape. And, so then you're totally right. So there should be something about that.
Okay, all right, thank you.
Yeah, thank you. Okay, so so this is just a microscopic definition. And today I will mainly concentrate on this macroscopic description of topological order. So basically the proposal is that the topological order are described by this topological extension over the ground states. And those topological extensions are described by so-called braided diffusion category. It turns out that the braided diffusion category, this category theory, happen to be the right language to describe a topological excitation or any excitations. Okay. So in 3 dimensions, we can have a string-like excitation, and so which we call the associated with a simple object. And this one morphism would correspond to point-like excitation. So in this picture, so this surface is a word sheet of a string-like excitation, and this line here is a word line of point-like excitation. And so you can see that this line separate to word sheet is a one morphism and things like that. The 2 morphism in this braided diffusion 2 category would correspond to this local unitary operators. And so this excitation can fuse, can braid. So that gave us a braided diffusion category. So therefore, we think maybe the topological order is very closely related to the braided diffusion 2 category.
May I ask another question?
Yeah, please.
Earlier you emphasized hi Xiao-Gang, by the way.
Yeah. Hi.
Earlier you emphasized that you really need to take n to be large, the number of sites.
Yes.
But I think you need more assumptions. First of all, you need, as Xiao-Gang said, it depends how you take a more structure of the graph. Like, assume you want the graph to be the density goes to infinity, but also to be a finer and finer mesh, but in all possible directions.
Yes.
If you have, you cannot just add more and more sites in the x direction, but not more in the y direction. So it's not simply taking n to infinity.
Yes.
You need more restrictions on that, and that depends on assuming more information about how the graph is related to an underlying manifold.
Yeah,
so
I hope there's a
the graph
local
is
description
n1 times n2 sites.
Yes.
You can send n1 to infinity holding n2 fixed, and then that's probably not good enough because you need both n1 and n2 to go to infinity.
You are totally right. Yes. So so actually
the other thing is that it might also be that the limit depends on how you take n to infinity. For example, through even numbers, through prime numbers, and so forth. And that could affect the answer. And I don't see that in your definition. I think what you have in mind is that there is a well-defined limit where n in all possible direction goes to infinity. And it does not depend on how we take the limit.
So there's maybe let me remark on these two. First, we don't have a symmetry, and also I said n1, n2 in different direction go to infinity in different rate. It turns out that this ability to to dissolve, we call dissolve tensor product state. Your product state is very important because when you have a gap states which can dissolve these product states, the metric became unimportant. So this really gave rise to this liquid notion of liquid phase. And so therefore, so basically, so the nx, ny, they go to infinity with different rate, different speed, do not affect problem here because of because this condition is very strong, make things topological.
No, but imagine N1 doesn't go to N1 is held fixed and N2 goes to infinity. That's clearly not good enough.
Yeah, that's not good enough. Yeah,
That's
well,
not
one
good.
need a both.
And it might
Yeah,
also happen that taking N1 through even numbers to infinity and taking N2 through numbers that are a 1 mod 13 will give a different answer. So I think you need more assumptions to.
And for the second question, whether n is some, so indeed there's one assumption. It's actually very interesting. That is there should be a sequence of ni which go to infinity, and this is defined for the particular sequence. And then there is an issue about the different sequence may define different things actually. And I don't know whether I don't have an example without symmetry whether this particular whether one need to take a particular sequence of ni or not. Certainly with the symmetry, one need to take a particular sequence which coupled with the symmetry. So indeed, this part is there's a lot of subtlety in this microscopic definition, indeed. And but what I really try to point out is that this local unitary and this ability to dissolve product states, I feel this is the two key point. Other point would be it's really about this graph and what kind of sequence one should take for this graph. Yeah. So this is actually within this definition. If you go through these subtleties, you'll discover the fraction phase actually. And so actually fraction phase actually this ability to dissolve product state is a condition which rule out the fraction phase. Yeah. Okay. So so let's please.
Does this mean that only the gauge fluxes are your simple objects? So unlike in 2+1D.
Oh, I'll come back to that. So what is a topological excitation? You can see if you use some topological excitation to describe topological order. So what is topological excitation? So here we say that remember the ground state is defined by some Hamiltonian H0. So I have an energy gap. The excitation is defined by original Hamiltonian plus traps. We can imagine there's some Hamiltonian term delta H only act on locally near a point or locally near the loop. So the Hamiltonian with the trap also have a gap. And the degenerate ground state of below the gap is called this topological excitation, or more precisely, actually correspond to home space of a category theory. So this is a degenerate subspace. Certainly, we take a limit with the system go to infinity. When you have a loop, the loop size go to very large. Okay, so this kind of a home space. But however, here there's an important detail: whether the trap Hamiltonian to be local or non-local around the string. So for the point, it doesn't matter. The local, non-local is the same. But when you have a string like excitation, whether this trap Hamiltonian can be chosen to be local or non-local, just around the string. So if you actually this if you choose a local Hamiltonian, we can also define equivalence relation. We can deform the local Hamiltonian so that this gap do not close, and those give rise to the equivalent class of excitation, and that define the type of excitation. Or you can use a non-local Hamiltonian and using the deformation of non-local Hamiltonian while keeping the gap, which define the elementary type. So actually, there's a difference between type and elementary type, and this defined via local and non-local Hamiltonian. So, so the question you raised, like in the gauge theory, the gauge flux actually corresponds to elementary type, I think. So this really is a subtlety in higher dimension, and also in gauge theory, there's also a descendant excitation, which is not elementary type, which is basically like a condensation of some point-like excitation around the line or around the surface. They may form quantum Hall states or ferromagnetic states, SPD states, and etc. So those string-like or membrane-like excitation formed by those lower dimensional excitation is called a descendant excitation. And so the type of excitation would include this descendant excitation and also this elementary type. Okay. The one way to distinguish these two excitation is that this elementary type excitation, say two excitation with different elementary type, do not have a domain wall connecting them. So there's no morphism connecting them. But however, the two excitation differ by the descendant excitation. There's always a domain wall connecting them. But however, this domain wall can be gapped or can be gapless. So this so there's a lot of subtlety in the definition of topological excitation. So that actually they have impact on what kind of category theory we should use to describe the topology order. So this question, I don't know, may not be fully resolved. You know, so this is the subtlety. Okay, so for example, in one dimension, we believe that there's no non-trivial topology order, and all the excitation in one-dimensional space is a point-like. So there's no distinction of elementary type or type. So they just they only have there are no topology order, so there's only a trivial excitation, no other excitation. In two-dimensional space, we believe that the topology order are classified by the unitary modular tensor category, and the times Z. This Z is described invertible topology generated by the E8 states. And there's only one trivial type of string-like excitation. And because we don't have symmetry, there's no topology order, so there's no non-trivial one-dimensional phase. So therefore, the string-like excitation only have a one trivial type. And certainly, there's also trivial elementary type. And for point-like excitation, there can be non-trivial one, which is a modular tensor category. In three-dimensional topology order, in three-dimensional space, the topology order classifies something, which we're going to discuss today. And here something interesting happens. There's an infinite type of a membrane-like descendant excitation, because we can using the trivial excitation to make a quantum Hall states. So we have infinite number of quantum Hall states. And they all have a gapless boundary. They don't have a. They only have a gapless boundary for the chiral quantum Hall states. And certainly we can also using this trivial excitation to make a toric model or some other quantum double model. So there also a membrane-like excitation with a gapped boundary. So there's a important thing is that whether the category theory describing 3D topology order should allow membrane excitation with only gapless boundary or not. So this is one of issue. And from physical point of view, looks like a yes, but from mathematical point of view, seems it's kind of difficult to include those kind of membrane excitation with a gapless boundary only.
Sorry, I missed one point. So in 3D space, you talk about a membrane-like descendant, but what about in 2D space? There are also things like that, but you didn't think
in 2D space there's a string-like, but there's no non-trivial phase of string-like excitation.
But there are descendants, right?
No, descendant, they are trivial. They all belong to trivial class of descendant.
Okay.
So the non-trivial phase on the membrane belong to non-trivial class of descendant.
I see. Can you say again, how do you define the class? Is it defined?
Class means in physics, it means a phase. If you're using local unitary transformation to connect two membrane, They
I see.
belong to the same
I
class.
see. I'm with you now. Okay, thank you.
Yeah.
I see.
And for the string and the point-like extension in three-dimensional space, there's non-trivial type, also non-trivial elementary type. So this is a kind of some subtlety in three-dimensional space. And certainly the braided fusion category do not really classify topological order because there's invertible topological order. For the invert, so let me just go through this quickly. For inverted topological order, there's no bulk extension, and the braided fusion category describe a bulk extension. So therefore, the braided fusion category cannot see invertible topological order. But however, we believe that in 3+1 dimension, there's no invertible topological order. So we don't have such issue. So therefore, in 3+1 dimension, it's okay. There is a invertible topological order. It's not an issue. We can use a braided fusion category to classify topological order. Okay, so let's try to see what is the structure of 3+1D topological order, or in terms of what is structure of this braided fusion category, braided fusion 2 category. Basically, the 2 category basically means that you have a string extension and there's a particle extension, and they can fuse and braid. But in 3 dimensions, the braiding of a particle is very simple because in 3 dimensions, we can only have a boson and a fermion. And in particular, moving one particle around another particle by 2 pi is nothing. And so they always have a trivial mutual statistics. So the trivial mutual statistics tell us that this particle form so-called symmetric fusion category. So this is a fancy way to say everything have a trivial mutual statistics. And also due to Tanaka duality, this symmetric fusion category is always associated with a finite group. So this symmetric fusion category can be viewed as a fusion of a representation of a finite group. So therefore, the particle in 3-dimensional topological order always give us a finite group. So we already have a finite group. We call it a G. Okay, and but however, the symmetric fusion category also have 2 versions because it have a trivial mutual statistics, but the self statistics can be boson fermions. So if a self statistics, if every extension, if all the point extension are bosons, then this is symmetric fusion category are really just representation theory of a group. If some particle are fermions, then this symmetric fusion category is this graded the super representation of a group. So this group would have a Z2 center and this Z2 center representation with non-trivial Z2F would correspond to fermions. So therefore, the 3+1D topological order would already contain a group or this kind of a graded group. So describing for the boson case or fermion case. So let's consider these 2 cases separately. And so the key to understand the 3D topology now is just to see what is the strings and what is structure of string, how the particle and string combine together. So basically, there's two things we are going to use.
Excuse me, Xiao-Gang.
Yeah, please.
How about the braiding between strings or multiple strings?
Yes, it have that. Yes.
But you only describe particle and string braiding.
Yeah,
here.
so I'm going to describe string now. So far I only describe particle braiding. I did not touch string braiding. And you are right. The braiding between strings is complicated, and it seems it's pretty difficult to understand the braiding between strings. So what I try to do is that I try to avoid this problem, find a way to avoid this problem, not to discuss in braiding between strings. So the two conjecture, or maybe 2 things we are going to use, which we believe, but probably may not be proven rigorously. One is this so-called remote detectability principle. That is anomaly-free topology. Again, anomaly-free here really means something realizable by lattice model. Here I use a definition. Realizable by lattice model in the same dimension means anomaly-free. Okay. Then for the anomaly-free topology order, every elementary type of extension can be detected by other extension via some kind of remote operation like a braiding. So this is how we detect a loop extension using a particle braiding. And then there's also anomalous topology order. So there are topology order which do not satisfy this condition. And but however, we believe that those anomalous topology order are always realizable by the boundary of some one higher dimensional anomaly-free topology order. So basically, this braid fusion category describing extension in anomalous topology order, which you denote as R. Actually, this R have a center or bulk, which gave rise to the non-degenerate braid fusion category, which describes topology order in one higher dimension. And we believe that such connection is a one-to-many. So basically, this boundary topology order R uniquely determine the bulk topology order. But the given bulk topology order, they can have many boundary topology order, but the boundary uniquely determine bulk. So these are two things we feel is most important that we can use in these two property to determine the 3+1D topology order without using too much of loop braiding. The loop braiding is more complicated.
Xiao-Gang, so a quick question. So do the higher categories in the previous slide, do they contain the descendant or not?
Yes, actually, to have a more complete definition of all this notion for center and all this category, one need to contain descendant. Actually, this is a very important work by Theo and Giotto, and they had a convention completion. And so after this convention completion, one can define this structure more rigorously.
But 3+1D and higher, does that mean it has infinitely many objects? Because as you commented earlier,
exactly, yeah. So thank you for the question. Actually, this is one thing which I myself kind of confused about. Even for the trivial topology order in higher dimension,
right,
it have a infinite number of descendant extensions.
That's right.
Actually, the descendant extension in higher dimension topology order classify all the topology order in lower dimension.
Yeah.
And so knowing the structure of descendant extension in higher dimension topology order, then we know everything. So that's n-vec. If you know n-vec, we know everything. But there's a issue where the n-vec contain descendant extension which do not allow gap boundary or not. This became an issue. Because including descendant extension which do not allow gap boundary is difficult. And because my understanding that currently the mathematical definition, those kind of descendant extension with only gapless boundary, I think is not included. But you know, I don't know enough of math to really see it. But this subtlety bothers me. Yeah.
Okay.
So actually there's a program driven by Liang Kong and Hao Zheng. They really try to include the gapless states in the picture. So therefore to have a complete theory of this higher category theory for topology in a higher dimension, one probably necessarily include the gapless states. Problem cannot avoid that. But avoiding that maybe also give you consistent mathematical theory. You know, what I try to say that there's another way to define descendant extension. We only include descendant extension with a gapped boundary. And that's maybe enough to define a consistent mathematical theory, some higher category theory. But this theory may not be what exactly corresponds to physics definition of topology order, which I gave in the microscopic sense. Yeah. So there's a lot of progress. Maybe there's still a small gap. Yeah.
Okay, thank you.
Yeah.
Can I ask a question?
Yeah, sure.
Yeah, so regarding this definition of elementary type of topological excitations, when you say a topological excitation, do you include things like defects? But when you say, for example, in 2D space, there's only one elementary type of string, I guess you're excluding, for example, these non-trivial invertible domain walls. Is that the correct understanding of the statement?
There's no invertible domain wall because of no symmetry.
But given a TKFT, it might have some intrinsic symmetries. We can construct domain wall that permutes.
So
citation.
here, okay, yeah, that's let me see. Is this
Chemo, maybe I can answer your question. I think the symmetric defect one is the condensation descendant in Xiao-Gang's setup.
Oh, okay.
Yeah, it's connected to the non-trivial one by introduce a twist defect, right?
Well, I guess my question is: do you include twist defects in this topological excitation? Or maybe I didn't quite get what you.
I guess when Xiao-Gang made elementary, you don't include it, but if you include the condensation descendant, it is included.
Yeah.
Okay.
So you're totally right. It's thank you for this question. Actually, there's a one thing. It's really about this definition. You can see when adding this traps, which define string-like excitation. So there's an issue. What can be realized by the trap? So one thing one can say that this trap probably do not realize the domain wall between two different topological order.
Sure. Yeah.
So I don't know this. Actually, the question you asked is a very good question. Whether this permutation anion, this kind of domain wall can be realized by the trap without modifying the Hamiltonian on the two sides. Or maybe this is a more delicate question. Yeah, indeed, this is a very good question.
I think twist defects.
I have a somewhat related question. I don't understand what kind of symmetries you assume exist.
No symmetry at all.
No symmetry. But it's often the case that the TQFT that you get at long distances has its own symmetries.
Yes, that's
even
right.
though they are not present on the lattice.
Exactly.
For example, in the Tori code, we have a Z2 times Z2 one-form symmetry, the TQFT, which does not exist on the lattice. But that allows you to have more defects along the line that Mong had in mind.
Yeah.
All sorts of other things, even though the microscopic theory does not have the symmetry. So you should be able to accommodate them because they're clearly properties of the system.
So yeah, the thing that whether this the question is really whether those domain wall or those line are they stable along this by this deformation, because we have this lattice Hamiltonian which can excite this high energy excitations. They can deform each other basically, and when you have a non-trivial topology order, as I mentioned that, then there's so yeah, we have non-trivial topology orders. Actually, those point-like excitation have this emerging symmetry. They can form this descendant excitation. Yeah, so that's why in three-dimensional topology order, there's a lot of descendant excitation on the string and on the membrane, which are formed by the gauge charge, for example. And the gauge charge have emerging symmetries, and so therefore those descendant excitation would have this SPD states and would also have this topology order states. Yeah, and yeah, so those kind of things would exist. Yeah. Okay, so the point is that we try to so let's consider a simpler case. the topological order is this with only this all the particle is only bosons. So suppose this particle there's no fermion, all the particle like excitation are bosons. So here the claim is that this kind of topology are described as so-called a one-to-one classified by so-called pointed fusion two category with only trivial morphism. And this kind of pointed fusion two category is given by this pair finite group and H upper for a cocycle. So this basic diagram Witten model. So the idea is that certainly we assume there's no non-trivial, no invertible topological order, and also the key step in the argument is that each of these is all boson topological order have a unique gapped all string boundary. So boundary only have a string, no particle, no non-trivial particle. Then the string on the boundary have a pointed fusion rule. So all the string have quantity dimension 1. And they form a group. This pointed fusion rule define the fusion group, this group. And this group on the boundary for the boundary string is equal to the group for the bulk given by this Tanaka duality of a particle fusion. Okay. And so this basically is argument. So certainly there's the topological order also have all particle boundary in 3+1D, but we find this all particle boundary of 3D topological order is called the pre-modular tensor category, and this all particle boundary is not very convenient. So we kind of try to avoid this using this all particle boundary to describe topological order. We try to using all string boundary. Okay, so how to construct an all string boundary? And the way to construct all string boundary is basically we try to condense all the particle like excitation. Yeah. Then if you condense all the particle excitation, then you change the topological order to another topological order. And this new topological order, because all the particles are boson, they're all condensed. So the new topological have no particle, have only strings. And here is one thing is that we try to show that this string only topological order in 3+1 dimension must be trivial. Okay. And so there's an argument. So we consider loop this S1, this loop S1 is our string excitation. We just put this S1 in the space. We assume space is S3, and then we say that if this S1 is non-trivial, it must be detectable by something else. But we only have a string, so this S1 embedded in the 3-dimensional sphere must be detectable by another loop. Okay, and these two loops can braid like this. Okay, and then you can shrink the inner radius of the loop, make it a very small loop. And then this braiding process can be viewed as a small loop going through this going to the middle of the first loop, and then braid through. And because our space is a 3D sphere, this can be viewed as a small loop go around our original loop. But the small loop can reveal the particle, and all the particles are trivial. So this became a trivial particle braid with a small loop, original loop, which is a trivial. Okay. So therefore, so this should say, yeah, we have nothing to detect this non-trivial string, and so this is the argument to say that if you condense all the bosonic point-like excitation, and we should get a trivial excitation. So this actually is you can say it's a conjecture, and so that's one of conjecture we use.
I think there's a question in the, yeah, Juven, please go ahead.
I'll try to understand the remote detectability, and also the statement here. Is it possible just have a topological order in 3+1D that have a string excitation, and they can be detected by braiding only through multiple strings, not the two strings process you described here? It seems like you are exclude those cases, right?
Yeah, here I try to argue each of the string, each loop string must be trivial. Yeah, indeed, we only argue that, and then we say that. So then we try using to argue that there is no non-trivial string, because if yeah.
But it seems maybe is it assumption or it's proven? It seems to me it's assumption.
It is an assumption, you know. I don't want to honestly. This argument is very strong, but this is a assumption. You can say this is an assumption that we try to say that the loop only topological order is particular if there's no particle. If there's no particle, the loop only topological order is a trivial.
I could hypothesize. I don't know whether you can rule out, say just one type of strings, and the strings only 3 of them braid through this 3-loop braiding can give some non-trivial statistics, and they will not be captured by what you described here.
No, yeah.
Right. Okay.
Yeah.
Thanks.
But
I have a question.
The thing that the 3-loop braiding actually really describing non-trivial dimension reduction. Yeah. And so
yeah, but there are maybe some other types of string braiding.
I wanted to ask whether 3-loop braiding counts as remote because they're sort of still linked together, right?
They don't touch. The remote means this particle never come close to the loop. So our probe is very far away from what we detected.
So you'd still count 3-loop braiding as a remote.
Yeah, the remote. They because of the string never come close to each other. So 3-loop braiding should be viewed as a remote. Yeah.
But following up on this question, Xiao-Gang, can you give us some intuition why you think there's no consistent topological order with only strings and they only braid non-trivially through 3-loop braiding? Because the argument on your side doesn't apply, right? Because in the 3-loop braiding, you will have a third string piercing through the center of the 2 of them, and then you cannot shrink S2 to make it a particle.
No, you cannot. Yeah.
So I'm curious about what's your intuition behind
the intuition is really that I feel that I don't have too much intuition here. I feel that this in order for string to be non-trivial, I think you can detect the single loop. I feel that this a single loop in S3 should be detectable.
I feel like this is assumption, not the.
Yeah, this is assumption. Yeah, this is assumption.
I think it's a simplification.
Assumption. Yeah.
Okay.
Yeah. So there's a this is the assumption built into this argument, you know, and yeah. So basically, that's the purpose of this talk. I try to expose all these assumptions and in this argument, you know. There's also dimension reduction. I think we can also use a dimension reduction to consider this, and which may give similar results. Yeah, it gives the same result. Let me say. And so therefore, if you condense all the point-like extension, then we'll get a trivial topological order. The domain wall between trivial topological order and non-trivial topological order would only have a string because all the particle condensed. So this is how we get this particle only boundary. Okay. So then how to understand this? How to get a string only boundary? You know. So how to understand this string only boundary? And again, there's a conjecture or assumption, because we need to understand what is a simple extension, and means stable extension without accidental degeneracy. And here we assume that if we can consider a loop extension, loop-like extension have a topology of S1, a loop. if you shrink this loop and to get a identity, maybe multiple identity, and then we say that this loop is simple with only if n equal to 1. Okay. And certainly the loop may shrink to something do not contain identity. And that means that this loop actually carry gauge charge. So we don't consider that case. We consider this a loop which have neutral charge. You can get identity, but the multiple identity means the loop is non-simple. And this again, from motivation that in 0 dimension, S0 actually has 2 points. It's basically a particle and anti-particle. And when you shrink this S0 into a point, and we get a single identity, that's condition for the I to be simple. And also in, for example, in 3+1, in S3 gauge theory, in 3+1 dimension, we find that there's a A1, A2 just repetition for S3, which are charged. And S3 also have a two conjugate class described flux, which are B and C. And both B and C, when they shrink, they get single identity. And so this seems kind of consistent. So we kind of assume this is another assumption we use. And
so this all string boundary may not always exist, right?
What?
The all string boundary may not exist for
they
every.
Exist. No, in this case, that exists. For the AB topology order, they always exist. This is what I try to argue. When you condense all the particle, you get a trivial phase. Then the boundary between this particular condensation-induced boundary is the all string boundary.
Thank you.
The boundary produced by condensing all the particles. Because particles are bosons, we can condensing all of them. Okay. So let's consider the string and the bulk. So we have a loop in the bulk. And if they shrink, they can shrink into the trivial particle and some ij non-trivial particle. So the S is a string. Okay, when they shrink, you get this. But when you bring this string to the boundary, it may become string may become a direct sum of several other strings on the boundary string. So H is a boundary string. This is possible. So here I try to say that the simple string on the boundary H should shrink to 1. If they shrink to n minus n1, n copy of 1, they will be not simple. Okay. So therefore, from here we can see that this simple string on the boundary, they all have this they have this dimension 1. Okay. If they have the quantum dimension 1, and then the reason is that on the boundary they can only shrink to 1. There's no other particle like extension. So therefore, when I shrink a loop to the boundary, the only thing we can have is a 1, a trivial particle. And this trivial particle should only appear once if this boundary string is simple. Okay. So this led to the argument that the fusion rule of boundary string is pointed. There's no direct sum on the other side after fusion. So therefore, the fusion of boundary string form a group. This group is called H. And this basically some of the important argument. So you can see that the bulk particle using Tanaka duality, we get a string. We get a group G. The boundary string using the fusion, we get a fusion H. And then next thing we try to argue this bulk, the boundary string fusion group and the bulk this symmetric fusion category group is really the same. It's same group. And actually, this is the main part of argument. We try to follow this Tanaka's duality argument, try to put it here. It's kind of long and also technical, so I kind of skip here. But basically, it's using this half braiding between the bulk particle and the boundary string, and assume they can detect each other. Try to show that these two group is the same.
Sorry, Xiao-Gang, for the previous slide, can I have a quick question? How do you define the quantum dimension of a string?
Yeah, quantum dimension string again. Yeah, this is. Thank you. So here I'm using some kind of maybe unconventional way. I don't define quantum dimension string. I define quantum dimension for loop. somehow I always have a loop. And then I have many loops together, and they are total fusion space. We have n loop fusions, dimension of n loop fusion space. We take an nth power, give rise a quantum dimension of the loop. So here, because string have this, if a string as a segment is difficult, but here I'm really thinking I treated this string as a loops and really constructing fusion space of loops.
But how do you define it for loops? So the trajectory of a loop in space-time would be some two-dimensional worldsheet.
Yeah, but here I'm using this using trap harmonic. I can imagine I have a one-dimensional trap many loops, and then this trap harmonic have the degenerate ground state subspace. The dimension of this degenerate subspace is a dimension of fusion space of those loops, and the nth root of this fusion space is a quantum dimension when n go to infinity. Basically, we have n. Basically, we just have n loops, and then the dimension for fusion space of n loops, taking nth power, nth roots, then that's give rise to this quantum dimension of each loop. Another way you can use in the fusion rule, actually in this case, the quantum dimension of this string is a sum quantum dimension of those particles. That's also works.
Okay, I see.
So is it the evaluation on the sphere S2?
It's a certain dimension, but it doesn't matter because if we take n go to infinite limit, the degeneracy from non-trivial closed space do not affect this definition.
But Laksha, that's actually exactly the reason I asked. The expectation value of the worldsheet of a loop on the sphere is not well defined because you can always modify the answer by an Euler counterturn.
Mm-hmm.
This is in contrast to the expectation value of the Ward line of a particle. That's why I was confused how to define the quantum dimension for.
Yeah, so here I think we using ground state degeneracy, so not using space-time picture. So that means if using space-time picture, the space-time is the time direction is a circle with no non-trivial twist. So when you have non-trivial twist along time direction, there may be actual phase in the partition function with a worldsheet.
Oh, so you probably put it on the torus in space.
On the torus, the space, the time direction with a circle with no trivial, with a constant. So we're doing this only counting degenerate ground state degeneracy.
Okay, that makes more sense because on the torus you don't have the Euler counterturn now.
Yeah.
But one subtlety that Shuhan mentioned still exists, right? Even when you count degeneracy, because you can still put particles on the string.
Yes.
That particle may also give you some extra degeneracy.
Exactly. So this is a trouble for the loop. It's a loop may contain particles, and so one need to define some trivial the loop without particle. So it means when they shrink, you get identity.
Okay.
Yeah.
I see.
Indeed, this using loop, not using.
Other which is I think equivalent, but you could consider the algebra of these loops and and everything else, and the algebra just of everything else, and you have these two algebras, and there is a notion that is called the Jones index which is basically a notion of the dimension of this small algebra in the big algebra.
Okay.
That is basically equal to the quantum dimension in the examples that are known, and but I think it's a precise definition of the quantum dimension for any kind of set of extended operator. Thank you.
Yeah. Thank you for the comment. Yeah. Okay. So so to summarize that, if the conclusion for this is that if a particle excitation are all bosons, and using this assumption and this argument, we try to claim that they are one-to-one correspond to this O-string boundary with a pointed diffusion and with no non-trivial morphism. So that's really the point of fusion two category, and which is basically the Dagger-Witten theory. Okay. Well, so basically, that's all the 3 plus 1D AB, all boson topology order are classified and realized by Dagger-Witten theory. And as a consequence, that all the 3 plus 1D twist higher gate theory with all particle being bosonic are equivalent to twist 1 gate theory. Yeah, go ahead. Yeah.
Can't you consider Dagger-Witten theories based on 2 groups? Will they have fermionic excitation?
Yeah, you can. Yeah. So Dagger-Witten theory based on the 2 group. If there is no fermionic particle-like excitation, they are equivalent to Dagger-Witten theory based on 1 group.
Okay.
That's what we try to say here. All the higher group Dagger-Witten theory are equivalent to 1 group Dagger-Witten theory if there's no fermionic particle.
Okay, thank you.
I'm a little bit unclear about what is meant by 3 plus 1D Dagger-Witten theory. A Dagger-Witten paper is about 2 plus 1D. So what exactly is being meant here?
It's that paper have a lot of things, and here what I mean is there's a part of the paper describing this triangulation of space-time, the finite group, that part. If you think so, here Dagger-Witten really means the finite group Dagger-Witten theory, and that one that construction actually can be done on any.
Do you mean here the main point of that? First of all, Dagger-Witten is in 2 plus 1. But second, the main point of their paper was adding the H3 term. Do you mean here that you're just doing a 3 plus 1 dimensional gauge theory, or do you need?
3 plus 1 dimensional finite gauge theory with a omega-3 twist. That's H upper 4 twist.
With H upper 4. So that's not what's in their paper, or is it?
Oh,
it's an extension of what they did.
Yeah, it's an extension. Yeah.
Okay.
Probably,
so you need both ingredients.
Yeah. We need both. Yes.
No, I think Dagger-Witten also discuss higher dimension in the paper.
So then it's my mistake.
Yeah. So it's so all this twist higher gauge theory. It's related to this twist 1 gauge theory. So that's a wonderful consequence of that. And so let me just since time is up, so let me just quickly summarize the result for the fermion case. So actually, this is for the fermion case, that is where the some particle of the fermion. So therefore, the group have this kind of a structure. There's some Z2 times this GB with some kind of twist. And so this kind of topology we call the EF topology order. It's kind of emerging fermion topology order. And so the claim is that this emerging fermion topology order is described by the unitary point diffusion 2 category. But but here we have some non-trivial 1 morphism. So basically, we still claim that this topology order can be described by string-only boundary with some simple particles. Okay, and this string on the boundary have a fusion rule, which is given by the GB and the group extent. Actually, this is I should write this way. Yeah. It's a GB extended by some Z2. Okay, and there is some kind of extension problem, and so this is GB. So the boundary string, the GB, describes this elementary object, elementary string, and this extending part is describing this banana string, this period with superconducting string. Okay. And the reason we have this kind of descendant string excitation because we have a fermion. The boundary also have a fermion because the bulk have a fermion this bulk fermion become boundary fermion. Okay, so the boundary structure is a little bit more complicated. And in addition to the boundary fermion, we also have the bound this Majorana string also have this has its own boundary, and this boundary is gave rise to this another one particle excitation, which is a quantity dimension 2, a square root 2 Majorana zero mode.
But Xiao-Gang, sorry,
basically,
in the old boson case, you could have also talked about the descendants, right?
In the old boson, I think there is no descendant because the particles are trivial, and the trivial particle do not form a one-dimensional topological order. If there's a non-trivial one-dimensional topological bulk, you have a descendant. You have a bulk, you have a descendant string.
Right.
Yeah. The descendant string, because the bulk boson carry gauge charge, have emerging symmetry. So descendant string would have this SPT states and also symmetry breaking states. That's a descendant string in the bulk. But the boundary, because symmetry is all broken,
right.
So we don't have that.
I see.
So that makes things simpler.
I see.
So this turned out to be important. Okay. So so let me just skip this. So there are similar arguments. So the point I try to make is the following. And there are two situations. One is that the boundary is the boundary string. The fusion boundary string is just a GB times this Majorana string. So their combination is just really times, and in this case, I'm tempting to drop it. Actually, we can drop this, and so there's a one version of EF topological order where the boundary string have this simple structure. Part the two gauge group pi 2 is only Z2. Okay, and so this is a one type. But there's another more interesting situation is that the boundary string fusion have non-trivial. We have a similar thing. When you have a Majorana string, and because Majorana string is a descendant, we want to remove them. For example, we want to have a string which do not have a Majorana string attached to it. Okay. If you can achieve that, if you can choose a set of a string without a Majorana string, then we can see that all those strings, the three string junction would have no Majorana zero mode. Okay. But however, there is a 3+20 topological order, which is this is impossible. And so because whether a string have a Majorana string or not have a Majorana string, it's hard to say. It's a tosser. We can only say two strings differ by a Majorana string. It's hard to say which string have Majorana string, which string do not have a Majorana string. So sometimes we cannot consistently choosing a basis of string which they all do not contain Majorana string. And this kind of abstraction gave rise to this so-called EF2 topological order. But anyway, and so this kind of EF2 topological order and is really have been seen in the fermionic SPT states. And so there's a EF topological order and the fermionic SPT states is very closely related. And they can be obtained by gauging SPT states. So I would summarize the result as following. If you start with the fermionic SPT states, and gauge all the symmetry, then we'll get the bosonic topology order. And this will be so-called EF topology order. So we think this so actually result from this work really they are really very much like a Fermionic SPD state, have a close parallel to that. And it really suggests that maybe all the bosonic EF topology order can be coming from gauging the Fermionic SPD states protected by one group, just protected by ordinary group. Okay. However, we can also gauge in the Fermionic SPD state. For example, you can gauge part of a GB, not all the GB, just part of a GB. Then we get the Fermionic SCD states. If you gauge all the GB, then we get the Fermionic topology order with no symmetry. If you also gauge Z to F, we get this bosonic topology order, which is EF topology order. So looks like in 3D plus 1D, even topology order with a symmetry, at least with a group-like symmetry, can be understood in this more general setup. Yeah, thank you. That's all.
Thank
Thanks,
you,
Xiao-Gang.
Xiao-Gang, for amazing talk.
Yes.
Are there any questions?
Maybe I'll have one question. So can you comment on the relation between this classification conjecture and with Theo's recent work?
I think yeah, it's the only thing I can say is that this is what we just discussed. You know the Theos recently they have this they define this you can define so-called maybe braided, and this fusion 3 category or braided fusion 2 category, they have this my understanding is that it can be classified by this by the pointed fusion 2 category. Basically boundary, because this braided fusion 2 category or fusion 3 category describe the topology. Then for the boundary, you have this fusion 2 category, and then that's only for the boundary. And this using the boundary, you can characterize the bulk. So basically, it's like a Greenfield center relation. Say all those fusion 3 category can be viewed as some kind of center of some fusion 2 category. So that actually relate to that. And in this in today's talk, I try to expand that a little bit. Try to say what is a physical definition for topology order? What do we want physically? And there's a my understanding there's a little gap there. It's just which is discussed whether in the condensation completion should include a membrane extension with gapless, with only gapless boundary, whether how to handle that, and that is that became an issue. Yeah.
Right, but that's probably not a little gap, but an infinite gap.
Yeah, you can say it's infinite gap. Yeah. So there's a physical point of view from microscopic definition, and there's a mathematical theory go from macroscopic to macroscopic. You know, there's a macroscopic description of bulk topology order using fusion 3 category. There's also macroscopic description of boundary using fusion 2 category, and these two may have a relation. So this is something one can do mathematically. Mm-hmm. But whether there's how to see this physically, whether using microscopic theory, whether that corresponds to microscopic gap or not. So there's a there's still issue. I feel this very interesting. It looks like to complete the story, one need to include Gapley state. This perspective is very intriguing.
Right, right.
And I asked, can you give? Is it possible for you to just mention quickly, really briefly, what the history of this categorical S matrix is? Where does it first show up? So it seems like this categorical S matrix is somehow crucial to the classification, right?
I really don't know. The earliest symmetry, earliest thing actually maybe is a more Steinberg is a rational conformal field theory, which link conformal field theory with a module tensor category, and all this conformal field theory. That's ST matrix is well studied, and then actually the name modular may come from there. So yeah, so maybe that's one of early work.
I think for the higher S matrices, there's this work by Reuter and Theo, right? That's upcoming, and Reuter has been giving talks about this.
Yeah, I was trying to connect the two. That's what I was trying to do.
Yeah, but I think this is unpublished work, so I don't think you can read it in the paper. I think maybe one comment about what Xiao-Gang was asking also. So I think maybe you're referring to this paper that maybe Theo has been in circulation, right? But I think he gave a talk a few weeks ago. And this sort of classification, which Xiao-Gang was talking about into EF 1 and 2. Basically, this EF2 is sort of what he would call this Majorana layer, and that's sort of what he would say is beyond sort of Dyker-Witten.
I see.
But I think it's sort of largely
that one
consistent.
Probably beyond Dyker-Witten, yes.
I see.
But it seems to be in agreement. That was my take on it.
But let me see. Actually, I don't know whether they're really beyond Dyker-Witten or not, in a sense, whether there's a Dyker-Witten model with a higher group, finite higher group, whether I thought about it a little bit. I couldn't see why that one cannot realize EF2. You know, that's
that seemed to, however, be the claim, I think, of theirs.
Yeah, that'd be certainly not Dyker-Witten for the one group, but Dyker-Witten with a arbitrary higher group, whether there's some chance. Yeah, I don't know. Yeah, those are interesting open questions. But this is a very also intriguing. That's fragmenting SPT. Basically, it's just a topological term, like a Weissman-Witten term. It's a topological term. So this claim is that there's some more generalized version of a topological term, which when you add them, so this Dyker-Witten model, there's this H-upper-4 can be generalized to something, some harmonic H-upper-4, and that's basically gave rise to this generalized topological order. Yeah, certainly. Yeah, this picture in higher dimension, I don't know. Yeah, 3 dimension seems it's too simple, surprisingly simple, and it's a surprise. But maybe in higher dimension, maybe in 4+1 is not that simple.
Any more questions in the chat? Maybe if you have a question, feel free to unmute yourself and ask it. Okay, if not, then maybe let's thank Xiao-Gang again for the very nice talk.